Ask My Instructor 4.3.17. Analyze the function f of x and then graph it. As we work through this problem, you will at times need to stop the video to work on the problem with me, particularly as we get into the algebra pieces. The first question we ask is, does the function have symmetry of some kind? To check symmetry, we look at f of negative x. Notice that f of negative x simplifies to negative f of x. When f of negative x equals negative f of x, we know that our function is symmetric about the origin. What about the domain? This is a rational function, so the only points not allowed in its domain are points where the denominator is 0. Solving for x squared minus 4 equals 0, we get our domain. Are there any intercepts? If so, where? To find the y-intercept, we evaluate f of 0. We find that 0, 0 is the y-intercept. Notice that 0, 0 is also an x-intercept. Are there other places where the graph of f crosses the x-axis? To find x-intercepts, we set the function equal to 0 and solve for x. For this particular function, when we set f of x equal to 0, we get one solution, x equals 0. And this gives us the point that we already found, 0, 0. So 0, 0 is the only x-intercept. What about vertical asymptotes? Well, to look for vertical asymptotes, we're looking for points where the denominator is 0 and the numerator is not. We already know that the denominator is 0 at 2 and negative 2. Notice that these values do not make the numerator 0. So there are vertical asymptotes at 2 and negative 2. What about horizontal asymptotes? Well, as x goes to infinity, the function goes to 0. Likewise, as x goes to negative infinity, the function goes to 0. So the function has one horizontal asymptote, and it is the x-axis. Where is the function increasing or decreasing, and is there a local extrema? If so, where? We first find possible critical points. For f prime of x, I have to use the quotient rule. After I find f prime of x, I look for where f prime of x is 0 or where f prime of x does not exist. It is not possible for f prime of x to be 0. Moreover, the only place where f prime of x does not exist is at 2 and negative 2. But the function is not defined at these points, so they cannot be critical points. So, if there are no critical points, that means that there are no local maxima and no local minima. We now evaluate f prime at a test point for each interval of the domain. So I have 3 intervals in my domain, and for the first interval I look at negative 3, and for the second one I look at 0, and for the third one I look at positive 3. And each time I discover that the function is decreasing. So this is a function that is always decreasing. Where is the function concave up and where is it concave down? To study concavity, we need to find f double prime. this next step is takes some difficult algebra, so again you may need to slow down the video or pause it. First, I use the quotient rule. Next, I'm going to factor out 2x times x squared minus 4. I'm going to factor that out of the numerator. And after I've done that, I'm going to cancel the factor x squared minus 4 out of the numerator and out of the denominator. So in the denominator, I'll have it just to the third power. I also have some simplifying to do. After I do that, I get f double prime equals 12x times x squared plus 12, all of that over x squared minus 4 to the third power. And we now set f double prime equal to 0 and solve for x. We get one solution at x equals 0. So there is one possible point of inflection, and that possible point of inflection is at 0, 0. Break the domain of f into subintervals using 0, 0. Recall what your domain is in order to do this. Okay, so we have a possible point of inflection at 0, 0. I keep saying 0, 0 because when x equals 0, we have already discovered that our function is equal to 0 as well. After we break the domain of f into subintervals, we choose a test point in each subinterval, and then we evaluate f double prime at each test point. And by doing that, I find the concavity. If f double prime is negative, we could have concave down. If f double prime is positive, we have concave up. So there is a point of inflection for x equals 0, and so the point 0, 0 is a point of inflection. Okay, and this slide summarizes the what we have found. You may want to stop and read this more carefully. But on the next slide, I'll show this information to you in graph form. I think it's a little bit easier to follow. Have my asymptotes, my concavity, my function's always decreasing because the first derivative is always negative. I have my inflection point, which is also my intercept, my only intercept. And then what I'm going to do is for each subinterval, I'm going to evaluate the function at some point in that subinterval. You can do it for more. I'm just going to do it for one though. And these green dots are locations on my graph. Okay, so I have points. For each subinterval, I have points. And I also know for each subinterval which direction the function is going and what type of shape it is. So these curved lines that you see, you want them closer to your dots, and you also want them to point in a decreasing way because our function is always decreasing. I'll show you what I mean on the next slide. So I kept the concavity that I had. So go back, look at the concavity. I have concave down, up, down, up. So I kept that, concave down, up, down, up. But what I did is I tipped them so that they're in line with the slope always being negative, so the function's always decreasing. And then I'm also paying attention to the fact that I've got these asymptotes. I've got an asymptote at the x-axis, I have an asymptote at -2, and another asymptote at +2. And once you do that, you really can fill out the rest of the graph. And it's hard for me to draw on your slide right here, so I'm just going to use a Wolfram alpha graph to show you my result. And so you can see the concavity down, up, down, up. The function's always decreasing. It has a horizontal asymptote at x equals 0, and it has two vertical asymptotes. The function has symmetry about the origin, and 0, 0 is the only intercept for x, and it is also the y-intercept. All right, well, hopefully this will help you with that homework problem number 3 that you have, and also give you an understanding of how one goes about analyzing and graphing a function. Take care.